Welcome to the world of particle physics. Today, we explore the cyclotron, a compact yet powerful device used to accelerate charged particles to immense speeds. By combining magnetic and electric fields, it allows us to probe the fundamental building blocks of matter. Why do we need cyclotrons? They are essential for producing medical isotopes and providing proton therapy for cancer treatment. By accelerating protons or ions, we create high-energy beams capable of precise medical intervention and deep scientific discovery. The cyclotron consists of two semicircular hollow metal containers called Ds. These are placed in a vacuum chamber between the poles of a powerful electromagnet. An alternating voltage is applied across the gap to create an oscillating electric field. A uniform magnetic field is applied perpendicular to the plane of the Ds. According to the Lorentz force law, this field exerts a force on moving charges, causing them to move in a circular path. The magnetic field does no work, it only changes direction. While the magnetic field steers the particle, the electric field in the gap provides the energy. Every time the particle crosses the gap, the electric field pushes it forward, increasing its velocity and kinetic energy. The field must flip direction periodically. As the particle gains speed from the electric field, its orbital radius increases. This results in a characteristic spiral path. Despite the increasing radius, a remarkable property of the cyclotron is that the time taken for one half-circle remains constant. The frequency of the particle's orbit, known as the cyclotron frequency, depends only on the charge-to-mass ratio and the magnetic field strength. This allows the alternating voltage to stay at a fixed frequency, synchronized with the particle's motion. For the particle to accelerate, the electric field must reverse polarity exactly when the particle enters the gap. This resonance ensures the particle always feels a push in the direction of its motion, regardless of how wide its orbit becomes. Let's look at an example. If a proton moves at 2 million meters per second through a 1.5 Tesla field, we calculate the magnetic force using QVB. This force acts as the centripetal force keeping the proton in its circular track. Notice that if we double the velocity of the particle, the radius of its path also doubles. This linear relationship ensures that even as the particle travels faster and covers more distance, it arrives at the gap at the exact same time. Each time the particle crosses the gap between Ds, it gains kinetic energy equal to its charge times the potential difference. Over hundreds of revolutions, these small increments add up to create a high-energy particle beam. The maximum energy a cyclotron can provide is limited by the physical radius of the Ds. Once the particle reaches the outer edge, it is deflected by a magnetic plate toward a target for use in experiments or medicine. There is a limit, however. As particles approach the speed of light, their mass increases due to relativity. This changes their orbital frequency, causing them to fall out of sync with the electric field. This is why standard cyclotrons have a speed limit. To summarize, the magnetic field bends the path into a circle, the electric field accelerates the particle in the gap, and the constant frequency of the AC source keeps the system in resonance as the particle spirals outward. Think about our frequency formula. If we increase the magnetic field strength, the particle is forced into a tighter, faster turn. Since the frequency is directly proportional to the magnetic field, doubling B will double the frequency. The correct answer is that the frequency doubles. This principle allows engineers to tune cyclotrons for different particles and energies, making them one of the most versatile tools in modern science and healthcare. Thank you for exploring the physics of the cyclotron with us. From life-saving medical treatments to fundamental research, these machines continue to accelerate our understanding of the universe. Generated by Vision Solve AI.